we've had some really nice talks about Bayesian inference, about MCMC. Amr talked about some big data stuff. What I want to get into today is when we take these MCMC methods, when we take these kind of generic things that work okay in 1, 2, 3 dimensions, and you try to push them to high-dimensional systems, the big systems that we're kind of interested in applied statistics these days, a lot of stuff starts falling apart. And you have to be really, really careful to make things that work. So what we're interested in is building up kind of principled mathematical algorithms that, by construction, will work in these high-dimensional spaces. So what I'd like to do today is hopefully motivate why we need these very specific kind of algorithms and show you a lot of the pathologies that arise if you're not careful. So there'll be some math, but not a lot of math, mostly just ideas, right? So hopefully it should be nice and interpretable. And then that motivation will bring us into Hamiltonian Monte Carlo, which is a really, really nice, elegant framework for doing these kinds of structures. And then that's going to bring us into STAN, which is our implementation of HMC combined with a lot of very nice user-facing interfaces and state-of-the-art computational techniques on the back end to provide a platform for building these kind of high-dimensional, not quite big data, but large models in a very, very generic way. Cool? Everyone awake? OK, so this is how I think about model space. Models, it's this weird infinite dimensional space. But you can think about it very generically in a two-dimensional way. So we have the sample size, the size of your data set on one axis. And then you have the model complexity on the other axis, right? So this is a very nice way to decompose models. Because it kind of, you have classical statistics over here. And ideally, you'd have big data right here. Right? You would think about big data would be any model, whether it's simple or complex, provided that we're looking at this regime of lots and lots and lots of data. Right? But this is not what big data tends to be in practice. In practice, big data is just this little guy down here. Right? If you think about the canonical big data regimes, it almost always comes down to MapReduce. And MapReduce is really, really simple models. Right? Amir talked about it yesterday. You have to have these abelian operations. MapReduce essentially counts. Right? That's all MapReduce does. And so if you have anything that's nonlinear, it's not going to be within the canonical MapReduce scope. And so there's been kind of an interesting evolution. Why is there not population in the top right part of this graph? Right? Naively, you would think that as we get more data, we can support more and more complex models and start asking more interesting questions. And indeed, if you look at what happens kind of classical statistics, we do see that behavior. As we get more data, we get more model complexity. But eventually, we hit a computational threshold. Right? There's some point where we can no longer scale up the complexity of the model as we add more data. Now, what's interesting here is that we don't just get a saturation and stay at that saturation level. We actually get this turnover into this big data regime. So we have this proliferation of just giant, giant data sets and people fitting simple models on them just because there's this idea that you have to fit all of the data. And that's an interesting regime. There's some utility to that regime. But what I like to argue for is pushing up to the top here. Right? What we're interested in is not so much the data being a paramount object. We're interested in models being a very, very important part of statistics. So Neil talked a lot about this. When you bring in models, when modeling becomes a paramount part of your approach, you can bring in a lot of very informative prior information. You can bring a lot of informative structure. It can drastically improve your inferences. But that's just a practical thing. If you're coming from the sciences, if you're coming from someplace where a model actually means something, then you can't just go to big data. Right? You can't go to one of these giant astronomical data sets and say, oh, I'm just going to MapReduce it, because it's not going to fit anything meaningful for the science. So what my collaborators are interested in is pushing up. Can we take this curve and just jam it as far high as we can? Right? So we're not interested in doing these big, giant data sets with relatively simple models. We want to build a model that's meaningful and interesting. And then once we have that model, try to fit it the best that we can. Now, this is a hard problem. And there's no easy solution. But the most generic solution is going to be Markov Chain Monte Carlo. So Anne talked a lot about this, kind of introduced some of the concepts. But it's important when we want to go to these high-dimensional spaces, these very, very complex systems, we have to be really careful about some things. So I'm going to go over some of the motivations and the kind of practical procedures for doing MCMC and place a lot of emphasis on the places where things go wrong and the places we have to be careful about for these high-dimensional systems. Now, I'm totally with Neil Lawrence on the Bayesian frequentist thing. I'm just going to assume we're all Bayesians here. If you want to argue about that later, that's fine. But assuming we're Bayesians, we're going to do a very straightforward procedure. We're going to model our prior. We're going to add a generative model of the data, and then that's going to give us our posterior. Now, this is really nice conceptually because it's a straightforward process. But for practical purposes, this is a really, really important concept. Because everything that is part of our model is in the posterior, right? Now, this means that any kind of statistical question that we can ask has to come down to a manipulation of the posterior, right? There's no statistical test we have to bring in. There's no utility functions. There's no loss functions. Those have a role. But in terms of a raw statistical question, everything's in the posterior. There's nothing else. So that's going to make computation straightforward. But it's also going to mean that it's straightforward to, say, identify the assumptions that we've made in the model, right? We're doing statistics. There's going to be assumptions. So you've got to embrace that and identify the assumptions and then validate them. So we'll see very quickly in a little bit how we can do things like model validation, posterior predictive checks, cross-validation, et cetera, from this approach. So we have the posterior. The question then is, what is a valid statistical question, right? So if everything's in the posterior, and I have to manipulate it somehow to say something interesting, but what kind of things can I do to a posterior? Now, canonically, there's two ways to approach it. The one that's particularly popular in machine learning is to do something like a map estimate. So we're going to take our posterior density, we're going to find the point estimate that maximizes the posterior density, and we'll use that for prediction or summary or whatever we might want to do. And then there's expectations. So expectations, we're not looking at a point estimate, rather we're integrating over the entire space to give some global summary of what our posterior is telling us. Now, if I right now said you had to choose one of these two and you can only do one of them for the rest of your life, what are you going to choose? Who wants to optimize? Raise your hand. Who wants to integrate? Who's too shy to raise their hand? OK, it's roughly consistent. So what I'm going to argue for very, very strongly is that expectations are the only thing that makes sense. So optimizations are nice because they just require derivatives. They have all of these nice computational properties in simple low-dimensional convex models. In high dimensions, optimization is almost meaningless. And I'll show you some arguments for that. Expectations, however, are very, very rigorous, strong mathematical objects, and they're what's going to scale to high-dimensional systems. Now, the reason for that is mathematical, and I apologize prematurely for the math, but you have to do it. So the problem here is that when we talk about probability theory, we're talking about measures. Now, I know not everyone's done measure theory. I certainly hadn't done measure theory for a long time. The fundamental object we're talking about when we're doing probabilities is this way to map well-behaved events to probabilities, right? And this is an abstract object. It's not what we're used to manipulating and dealing with when we're playing, when you're writing code or when you're doing simple manipulations. What we're used to dealing with are these densities, right? And densities require a parameterization. So what it means is we have this abstract space, sigma, and we need some way to map it into the real numbers. Once we've chosen that mapping, then our measure decomposes as the density that we're used to dealing with and this differential volume element. But what's important to recognize here is that this density is dependent upon this parameterization. It is not a fundamental object. And so if you have any kind of manipulation that just uses this density but ignores the volume, then you're doing something wrong. And as we'll see as we go to higher and higher dimensions, this becomes really, really important. And this is where a lot of the pathologies arise. If we go back to the statistical questions that we had before, we have optimization, we have expectations. If we look at what they're taking advantage of, right, the optimization is optimizing the density. And that's the bad thing. So optimization is fine if you have a valid coordinate parameterization invariant object that you can optimize. So I'm not going to talk about it, but things like KL divergence, variational Bayes, there are ways to do this right. Just doing a map estimate is not right. But if we look at the expectation, right, we always have the differential here. Expectations just rely on the underlying measure. So they're kind of a foundational object. In fact, they're the only thing that makes sense from a purely measure theoretic perspective. So if we want to scale, thanks. If we want to scale these algorithms to high dimensional systems, we have to ask the right questions, right? That's the first important thing. Once we're asking the right questions, then we can worry about how to answer them in a useful way. So that first step is that we want expectations. And it's relatively easy to see what happens in high dimensions. So let me give you a little example. So this is the canonical example of high dimensional systems. Take 1 million Gaussian variables, IID, and I'm going to look at the radial component. So the density is going to have your standard Gaussian profile. Everything looks OK. But remember that the volume is important here. And the volume in these systems, if you think about a shell, right, the surface area of that shell gets bigger and bigger as you go out further and further. And that growth gets bigger and bigger as you go to higher and higher dimensions. So we have this competing volume increase. And so the mass, the measure, the product of those two is some compromise in between. And we get something like this. Right? So note that the mass is starting to move away from where the mode is. The mode doesn't mean anything in particularly useful in high dimensions. Right? This is what we want. So this is the generic property called concentration of measure. And it leads to a lot of very interesting statistical phenomena. But what's important here is it means that what we need to find, the parts of a statistical model that we're interested in exploring, are really far away from where we typically think they are, and they're not particularly easy to explore. So just to show that in practice, so this is Monte Carlo draws from a Gaussian. Again, just looking at the radial component. If I have one Gaussian flat density profile, right, there's really nothing crazy going on because the volume is constant. If I go to 10 dimensions, now I start seeing the aggregation. Right? Again, we're piling up away from 0. And as I go to 100, 1,000, 10,000, now we're getting a singular delta function-like behavior. In fact, as you go to infinite dimensions, this concentrates on a differential shell at 1. Now, this is kind of a toy example because there's enough symmetry that you don't have to worry about this. Right? You can just deal with all of the one-dimensional problems at hand. But when you have correlations, when there's nonlinearities in your model, this stuff gets really weird and really nasty. And this is what you have to be careful about. So if we want to have scalable inference, we need to be able to find the probability mass and then use that. Once we found the probability mass, compute these expectations. Expectations are basically everything we can do. And you may or may not realize it, but everything statistically is an expectation. Right? So summary statistics, means, variances, medians can be frozen in terms of expectations. Marginalization, which is perhaps the most important thing you can do in high-dimensional systems. This is any kind of big system gets solved by marginalization, right? It's one of the most important tools we have available to us. Conditionals, if you want to compute a conditional, you have to compute a marginal, which requires computing expectations, right? So all of the statistical questions that we're used to dealing with are integrals. And so in a very real sense, high dimensional inference and Bayesian inference isn't hard because conceptually it's hard. Right? Building a model isn't trivial, but it's a straightforward process. Computationally, this stuff is really, really hard purely because integration is hard. Right? That's it. That's the only reason why this stuff is really, really hard to do in these big systems. So what we need to do is be able to find a way to integrate high dimensional integrals very, very efficiently. Right? That's the only thing that we have to worry about. And this whole myriad of statistical algorithms are all attempts to compute integrals in high dimensions very, very efficiently. That's it. Right? So INLA is computing integrals. Expectation propagation is computing an integral. Variational Bayes is computing an integral. And as we'll see, MCMC is computing an integral. So remember that all we're doing here is integrating. Now, Anne talked about this a little bit. You got the history of MCMC is fun. He mentioned the infamous Metropolis, Rosenluth, Teller, and Teller paper. There's also a paper by Ulam and Metropolis and some other interesting ones from around the time. But I think it's an interesting story in the statistical literature, because that paper was 1954, something like that. It came out of the Manhattan Project. They were using it to measure these neutron diffusions to build a better bomb. And they had these really fast computers. And by that I mean they had rows of women with calculators, and they would do a calculation and pass it to the person behind them. That's what a calculator was, right? And that's not something anyone else had. And then as you go into the 60s and the 70s, physicists start building these giant, giant computers, and they're the only ones who have them. So you see these kind of Markov chain algorithms. They're oftentimes known as molecular dynamics in the physics, chemistry literature. And there's this whole proliferation of them. No word of it in statistics. There's a paper in the 70s by Hastings. Nothing happens. And it's important to recognize here that there's a resonance between algorithms and computation in statistics, right? You can have the best algorithm in the world, but if you don't have a computer to run it on, it's meaningless. And you can have all the computation in the world, but if you don't have a good algorithm, nothing's going to happen. And this uptick is the resonance of MCMC in the personal computer. Right? So there was this huge explosion, this revolution of Bayesian inference in the late 80s and the early 90s, where statisticians were buying PCs for the first time, and they were able to write these algorithms. So we take it for granted now. Everyone's got a laptop here. But it was a really, really big deal back then. So I know Anne talked about MCMC a little bit. I'm going to just review the construction. And again, I want to emphasize things a little bit more about things like convergence, things like ergodicity, and some of the analysis you do after the fact, because we're going to see this in Stan later on. So the first thing to recognize with MCMC is the Monte Carlo part. So Markov Chain Monte Carlo, what does the Monte Carlo mean? Monte Carlo refers to the fact that we're not going to deal with our measure or our density directly, but rather we're going to deal with a set of samples that are drawn from the measure. Now the reason we do this is because these samples represent the distribution. Right? The samples are going to be where all that probability mass is. So in some sense, it's kind of a dynamic grid concentrated at the places we actually care about. And what that manifests as is any kind of expectation that we might want to compute can be estimated by this Monte Carlo estimator. Right? So this is the canonical Monte Carlo estimate. If I want to know the expectation of f, I just average f over all of the samples that I drew. What's really important about this estimator is that its variance does not depend on dimension. So provided that I have the samples, the uncertainty of this estimator is the same in 1 dimension, 10 dimensions, 100 dimensions, 1,000 dimensions, 1,000,000 dimensions. It doesn't matter. This is the magic of the Monte Carlo algorithm. Now what's happening is that so there's no magic going on. All of that, I skipped over numerical integration, quadrature, right? If you're doing this naively, you'd put a grid down, right? You'd have endpoints on every direction. You form a hypercube with all of these points. How many points do you have in d dimensions? Yeah, n to the d, it's exponential scaling with dimension, right? So in 5 dimensions, maybe 10 dimensions, if you have a really fast computer, you can do a raw quadrature. But if you get to a real problem in a real number of dimensions, you just can't do that. And so what happens here is that the Monte Carlo integrator somehow is able to get 3, 4, 5 digits of precision in constant time. And then if you had to keep running, that exponential amount of time manifests in the 1 over n convergence of getting the 6th, 7th, 8th, 9th, 10th digit of precision. But who cares about those digits of precision? They don't mean anything in practice. So that's really what's going on here. So we nominally get this nice constant scaling with dimension if we have samples. But how do I draw independent samples from a distribution? So turns out it has the same exponential scaling as integration does. Right? It's the same process. It's the same exploration of this infinite dimensional space, or high dimensional space. And if you do it naively, you need to have that exponential scaling. So the trick to making Monte Carlo useful is to not use independent samples, but rather to use dependent samples. Right? Dependent samples are fine. We just have to take the correlation into account when we look at the estimator of this guy. And that's where the Markov chain comes in. So as Anne mentioned, a Markov chain is an operation that takes a distribution into another distribution. And if we're careful, if we tune it such that if we put in our posterior over here and we get our posterior out, that the action of this transition on a state is going to give us correlated samples. And so all we have to do is find a transition operator that preserves our posterior, and then we get the correlated samples that we want. We can plug them into the Monte Carlo estimators, and we get all of our Monte Carlo estimates for the expectations that we're interested in. Right, that's the entire process. Now, I want to go into a little bit of detail about how we do this in practice, and it's going to proceed in 3 stages. Who's run a Markov chain before? OK, good number of you. So most of you should be somewhat familiar with this. But I want to be really, really careful about it, because it's very easy to do MCMC wrong. One of the things that you see a lot when people give introductory talks about MCMC is there's this sense of magic, right? There's this, when people talk about things like convergence, it's like, well, it might work, it might not work. I can't tell you if it will or won't. And I often feel very unsatisfied by that, because you walk away being like, so is this an algorithm? What is it, a magic box that do I have to wake up and pray to the Markov gods that my chain's going to converge? And it's the problem I think ends up happening is the literature on Markov chains is really, really weird. It's very fragmented. It's mostly written by these very, very mathematical statisticians, and untangling that notation is a nightmare. And I know that because this is what I'm actively doing with some of my colleagues. It's really, really hard. So I'm going to try to give you some intuition about what's actually going on so that you can see that it's less magic and more just really hard math. So we have this convergence stage that Anne talked about a little bit. We have the sampling stage. Now, normally this is hands-off, but as we'll see, there's some things to be careful about. And then we have the analysis stage. So once we have the samples, how do we actually compute the Monte Carlo estimates? What are the variances? So I'm going to just briefly go over some of the things to be considered with there. The initial stage. Now, Anne called this burn-in, and that's the common use of description, vocabulary, whatever you want to call it. We don't call it that. I worked with Andrew Gelman for a little bit, and we're collaborators in Stan. And he's very particular about a lot of his notation. And this is a really important case. Burn-in means we're going to run something until it breaks. Okay, hopefully our algorithms don't break that easily. We're not trying to do that here. What we're trying to do in this initial stage is to equilibrate. Right? So we're warming up our system. So we started to call it warm-up. Hopefully you'll have seen some inertia into changing of the notation. But be aware. So what are we doing with equilibration, right? So again, if we start with the stationary distribution, we maintain the stationary distribution. So we have an invariance. The problem in practice is that I don't know how to start here. If I knew how to start here, I'd already be able to do what I needed to do. What you have to do in practice is this kind of filtering procedure, which is really awkward. So you start with some arbitrary distribution, and you start hitting this transition operator over and over and over and over again. And if you apply it enough times, you'll eventually filter out and just be left with the target distribution. So for example, graphically, we might start with a delta function. So we might have a single point. We have no idea what the actual distribution is. We apply the transition operator, and we get some nice Gaussian. And we keep applying it. And the Gaussian starts converging to some stationary distribution over here. So what we have to do is keep running until our distribution starts stabilizing. Now, the problem with this is that this is super abstract and not at all useful. Right? So when was the last time you wrote a continuous probability distribution, encoded every one of those continuous elements on a computer? I mean, it's just not. I mean, flash memory is good, but it's not that good. So we have to consider what we actually do. Right? We don't have this entire distribution in memory and deal with that. We have a state. Right? We're using a state to represent the distribution. And so what does it mean to converge from the perspective of a single state? So remember, Monte Carlo is computing expectations. And that means it has to find the probability mass. And the probability mass, as we saw in high dimensions, tends to concentrate in certain neighborhoods. Now I'm going to call that very loosely the typical set. So there's not a hard boundary that defines the typical set versus the non-typical set. This notation is kind of stretched from information theory, where in infinite dimensions, we get that concentration of measure, and there's a real well-defined thing. But so we have a vocabulary to talk about things, I'm going to call the typical set where most of the probability mass is. And so in terms of the state of a Markov chain, convergence is all about finding the typical set and then exploring the typical set. So to see that graphically, let's imagine this is a high-dimensional, symmetric Gaussian. Where's the typical set going to be? OK, middle, center. OK, no. So remember concentration of measure? Where's all the mass? The shell, right? So if I run a Markov chain, I don't explore to the center. I do something like this. And in fact, as you go to higher dimensions, this gets tighter and tighter and tighter. So the typical set looks something like this. It's not useful to ever actually visualize a typical set because you have no idea what it looks like. You have no idea how to confirm what it looks like. But intuitively, remember that a Markov chain is all about finding this thing and then exploring it. Right? That's all we're doing. Now, if we go back to the Gaussian case, remember that we have this kind of very, very generic behavior where the typical set is far away from the mode. A lot of times you see this suggestion to start a Markov chain at the mode, and everyone's like, OK, you're done. You're good. You don't have to worry about convergence. That's absolutely patently false. The mode might be an OK place to start in that it's closer to the typical set than like way out here in the tail, right? But you still have to converge because you still have to go from here to here. And in a high-dimensional nonlinear complex model, that's really hard. So there's no panacea. There's no initialization that's going to save you. You have to run the chain. So the question then is, how do we know once we found the typical set? And this is where the magic comes in, if you will. The problem is there's no sufficient condition for convergence. There's a lot of necessary conditions, but there's no sufficient condition. So all we're going to be able to do is apply every one of these necessary conditions and hope that we don't have a weird pathology that we're not dealing with. Right, so if we have a mode over here, there's a mode way over here, there's absolutely no guarantee we're ever going to be able to find that other mode. Right? It's high-dimensional spaces. It's measure zero of finding something way over there. So the first kind of obvious thing to do is look for visual stationarity. So you just run the traces of every one of your variables, and you see this kind of canonical behavior. You start off somewhere really far, you very rapidly pull in, and then you've hit an invariance. Right? It's clear there's been a change in behavior from here to here. And that's, again, it's necessary, but it's not sufficient. Because if I had run another chain, I would have gotten something like this. So what's happening here is that I have a multimodal distribution. So what we recommend is to run many chains from diffuse initializations and essentially do an ANOVA. So this is the potential scale reduction factor, more colloquially known as R hat. And this gives you a very nice, again, necessary condition, but not sufficient condition. And indeed, what we actually do here for Stan, which I won't have time to talk about, is we take these chains and we split them in subsets. So we're actually looking not just consistency amongst the chains, but also consistency within the chains as well. Because stationary should mean that if I take a chain split in half, those two things should look completely invariant to each other. So this is about the best we're going to do. I'm not going to talk about multimodality. Oh, thank you. We can talk about it later if you're interested. It's a different problem. MCMC is not going to solve multimodality. There are very good algorithms that can, but you should be using those algorithms and not MCMC. Now, another handy thing about warm-up is the adaptation of your Markov chain. So somebody was asking Anne about how do you choose the scale of the covariance in random walk metropolis. Now, I'm not going to agree with the answer he gave because we do know how to do it, right? There is a number, 0.234. It's the asymptotic, optimal, efficient step size for random walk metropolis in infinite dimensions. Infinite dimensions turns out to be 10, so it's good for most problems. And what we can do is tune it during this warm-up phase. So what we're actually trying to do is estimate a global expectation, use that to tune these properties of the Markov chain, and give us optimal performance. Once we start sampling, we can't touch these things anymore. If the Markov chain, if the transition operator changes, and anytime you tweak a parameter, you have a new transition operator, you can no longer guarantee that you're going to be sampling from the stationary distribution. There are ways to kind of sort of do it, but they ended up not working well in practice. So warm-up is all about finding the typical set. Once we found it, adapting a bunch of the parameters that we're interested in. These are parameters for HMC that we'll explore a little bit in a second. But the utility here is, as we're exploring, we're going to adapt these things and get very good performance. OK, so now we have the sampling phase. Now, sampling is typically a hands-off process. So we run our chain, we've converged, and then we just back off, right? The computer's just going to do its thing. But you have to be careful here. Markov Chain Monte Carlo is this tricky beast. And that if you look at the theoretical guarantees for when it works, it basically works for a Gaussian. Like literally, if you read the papers, they'll be like, well, if you're a Gaussian and you kind of have Gaussian-like tails, it'll work OK. The second you have a realistic model, it doesn't work. Or there's no proof that it works. And people tend to ignore this, and they'll run random walk metropolis anyways. And it looks like it works OK. But you're getting biased answers. And you have to be really, really careful at diagnosing your chain to make sure you don't have some of these pathologies. One of the ones that is kind of an interesting case study is something like this. So let's say I'd run 200 iterations. I get some motion like this. There's large autocorrelations. It's not great, but it's not too bad. I seem to be exploring reasonably well. But if I kept running, I get this wacky thing down here. Right? Clearly something is different about low parameters, low values of that parameter. And this is a little subtle. This is a manifestation of the breakdown of ergodicity. So ergodicity is kind of a two-headed coin. On one hand, it's the property that we can find the typical set. On the other hand, it's the guarantee that we can explore the typical set once we found it. And what's happening here is we found the typical set, but we can't explore it. There's a pathology at low values of this parameter. That means our chain can no longer explore the entire neighborhood. And what's interesting about this is a real model. This is a hierarchical model that people were using random metropolis on, Gibbs sampling on. And no one ever saw a pathology like this. The first time we saw this was when Andrew was running HMC, and because it was so fast, he ran it for 100,000 iterations because he could. And the next day he came back and he's like, my chain looks atrocious. What the hell happened? And what happened is that these algorithms are not ergodic in this case. And we only ever saw it because we had a super fast algorithm that we could run for 48 hours. So these things are subtle, but they're really important because they will bias your expectations. Right? Your lower medians here, or your lower quantiles here are completely off. And your expectations, depending on what you're looking at, can be off by 10, 20%. So we have these potential pathologies. And that means when we do the analysis, when we do the computing of the expectations, we also have to be careful with a lot of diagnostics. We're not going to have a huge amount of time to talk about some of the things, but I'll kind of briefly mention some of the potential things to look at. So we have our samples. We've run our chain. We have our samples. We're going to compute our Monte Carlo expectations. We've already seen this estimator. The really important thing is not this equation, but this equation. So the real utility of a Markov chain is something called the Monte Carlo central limit theorem. Under sufficient conditions, they're really mild. They're not too bad. Basically, F can't be something ridiculously crazy. The estimator for F converges to the true expectation, so it's unbiased. And then its variance is given by something called the Monte Carlo Standard Error. So the bias is not something we're particularly interested in. In practice, what we have to be careful about is computing the Monte Carlo Standard Error. Now that is given by the true variance of the function we're taking the expectation of, divided by something called the effective sample size. So if we had independent samples, this would be the number of counts, right? This is the standard variance of a mean estimator. So if we take the square root of this, we get the canonical 1 over square root of n convergence. But when we have correlated samples, we have to be really, really careful about what ESS actually is. And the way it gets computed is by looking at autocorrelation. So we have our chain, we have our correlated samples, and we can look at the correlation of every 2 point and just move that along. That gives us the lag 1 autocorrelation. That's here. We can also look at the correlation between a point here and a point 2 steps away, 3 steps away, et cetera. And that gives us what's called a correlogram. So this is the autocorrelation as a function of the time difference between points. And if we have a very nice chain, we get some behavior like this, where our autocorrelations immediately drop to 0, and they're immediately consistent with 0. So our effective sample size calculation, which is just summing up all of these autocorrelations, if these are all 0, then we just get n. Right? So in the case of no autocorrelations or very low autocorrelations, our ESS is effectively the number of samples that we drew. We're in a very, very efficient regime. We're essentially drawing independent samples. We can do very, very efficient Bayesian inference. If, however, we're in the upper regime, where we have very large autocorrelations, then sum is going to be very, very big. N is going to be really small compared to the, ESS is going to be very small compared to the number of transitions that we generated, and we're in a very bad state. If you're running something like random walk metropolis in a big, complex model, lags tend to go out to like 100, 1,000, 10,000. I've done examples where lags are non-trivial up to 1 million. And it's not uncommon. So one of the things that Anne very briefly mentioned was thinning. There's the paper by Geyer who talks a lot about how you deal with these things. Thinning is what happens when you have lags all the way up to 1 million. So you have 1 million samples, but they have the information of 1 sample. So you don't want to store all of that on a computer because it's mostly junk. What we'll see with Hamiltonian Monte Carlo is that you should never have to worry about that. If you're doing a good algorithm, you should not have to worry about these ridiculously large autocorrelations. So in the end, what you want to look at is some kind of summary like this. This is the output of command stan. Yep.
Yeah, so I'm always confused about this ESS because correlation is a linear measure essentially. So when you sample from a non-linear distribution, you get low correlation.
Right. So the effective sample size depends on the function that you're trying to estimate, right? There is no global effective sample size for the entire chain. The whole part of a Markov chain is that you're doing these expectations. So you have to compute effective sample size for every parameter that you're looking at. And this is tricky because we don't know how to look at things like multivariate effective sample size. There's literally no theory on that kind of construction. And we've tried to push into it a little bit, but it's really awkward mathematically. So the thing to remember, and this is a very good point, all of these measures, things like R hat, effective sample size, they depend on the expectation you're looking at. So you might have something that looks fine. You might have another expectation that has a lot of weight at very large values, and that might be more of a problem. There will be larger autocorrelations there. Right? So the autocorrelation is not so much a measure of your chain, it's a measure of your chain convolved with the function you're looking at.
So what do you think of this practice that everyone just computes kind of a ESS for every of the covariates with something perspective? I mean, that's kind of not saying anything.
Well, okay, so the question was, people will often just take the mean of all the covariates and just look at that. If all you care about is the means, then that's what you should be looking at. If you care about some other statistic, if you care about some combination of the variables, then you have to look at that combination of the variables. So for example, if what I cared about here was not mu, but mu squared, or some nonlinear transformation of mu, then I need to compute the mean, the Monte Carlo Standard Error, the effective sample size for that nonlinear function.
But then this also means that when you run your chain, you already have to be aware of the question you're asking for the sample, so you can't read.
So not quite. Okay, so the question was, do you have to know what you're looking at to compute these things as you're going? The beauty about Markov Chain Monte Carlo is that you don't actually have to do that. Because if you have all of your samples and you want to look at some nonlinear combination, you can just apply the nonlinear function to the samples and then do the Monte Carlo estimate. So you can marginalize, you can do nonlinear transformations.
But you have to stop your chain with respect to some statistic, right?
Not, well.
You don't just run it forever and then you say, okay, now I'm interested in this, now I'm interested in this. But you say, I'm interested in this, how long do I need to run the chain? Then you run it. And then if you look at something else, you might have to run it longer. Right.
So there are going to be subtleties where you might, for example, look at some wacky nonlinear combination with particularly heavy tails. Monte Carlo central limit theorem might break down, and you have to go back and run your chain. There will be cases like that. But for the most part, if you run, especially with these nicer, new, more advanced algorithms, once you find the typical set, it's very rare that one variable converges and the others don't. So in practice, that's less of an issue. It is something you have to be careful about, and that's why it's important to look at these diagnostics. But it's not too crazy. But that's a really important point, because there's a lot of algorithms out there that look at, they'll compute expectations and they'll average them together, or they'll do some kind of pre-analysis. And the second you do that, you can no longer have this nice transformation property. So any kind of thing where you might want to parallelize by running multiple chains and then breaking them together means you have to know exactly what you're doing beforehand. So if you know about ensemble samplers, Dream and Weave, or all these crazy things, those get limiting because you have to know what you're looking at. Same thing happens for variational Bayes, excitation propagation. You have to rerun that analysis every time you want to look at a different variable. With MCMC, you don't have to do that. And that's a really, really powerful thing in practice. Okay, so just to, again, summarize, say we're looking at something like mu, we get the mean, we get an estimate from the Monte Carlo Standard Error, so we have an actual idea whether this is a meaningful estimate. We get all of our quantiles, number of effective sample size per time. This is important if you want to compare algorithms. This is meaningless, time is meaningless. This is the only thing that actually means that is relevant in comparison. and then looking at things like R hat for convergence. Now, the only parameter here is mean, and then I have 4 of these random things here. I have LP, accept stat, step size, tree depth. These are parameters of the Markov chain. And this is where we start looking for pathologies that may show indications of a breakdown of ergodicity, of not fully exploring the typical set. Again, unfortunately, I'm not going to have time to talk about how we do that for things like Hamiltonian Monte Carlo, but we do have the potential to do it. There's enough mathematical structure that we can identify when things go wrong. And that's really, really important for these high-dimensional systems. Excuse me. So the last thing I want to mention on the MCMC side is posterior predictive checks. Have you guys heard of PPCs before? OK, who's heard of cross-validation? OK, so you've heard of PPCs. So one of the things that people worry about a lot from a Bayesian perspective is I have data, I fit it to the model, and everything's self-consistent from a Bayesian perspective, right? You assume the model's true, and you learn the parameters. But what if your model's not true? What if there's some wacky assumption that you weren't really aware of? This is what I was mentioning earlier about identifying your assumptions and validating them. How do we validate an assumption if the theory is internally self-consistent? Well, you have to apply additional assumptions. And the additional assumption that we're going to add is that we might want reasonable predictive performance. Now, this is tricky. We would love to be able to look at an entire ensemble of test data and say something interesting, but we can't. And so we want to look at predictive stuff. And in machine learning, you want to look at predictive stuff as well. But having a point estimate, having a single held out data set, gives you a very weak estimate of predictive performance. Cross-validation gives you no estimate of predictive performance. It gives you a sense of partitioning performance. So philosophically, just be aware that this is going to be something useful, but it's not going to give us a full predictive comparison, because we only have one data set. We only ever have one data set that we're looking at. So from the Bayesian perspective, what we do is we compute the probability of pseudodata given the data that we measured. And again, it's just an integration. And because we're doing Markov Chain Monte Carlo, the integration should come for free, and indeed it does. So we draw a sample from the posterior, and then given that sample, we draw pseudodata. So we just generate from a likelihood. And what this then manifests as is we can look at data space. So imagine we had a one-dimensional statistic. This is all of the pseudodata that we drew from our chain. And then we can compare that to the data that we actually measured. So if the data is consistent with the pseudodata, we have some indication that there's consistency of the model. We're not overfitting, we're not underfitting. Things look OK. Whereas if we had something out here, there's a little bit of tension. Either we measured a very rare data set, or our model is perhaps not fitting the data particularly well. And this is how you can formalize something like cross-validation. So you take this posterior predictive density, and given a certain approximation to this, cross-validation pops out. And this is really nice because you can understand the limitations of cross-validation, especially when you go to high-dimensional systems. But it's part of the Markov chain, and we'll see in the tutorial about how we calculate this in practice. OK, so I'd like to pause for a few minutes here to let everyone kind of absorb. We very, very quickly went over how we actually do MCMC in practice, worried about some of the pathologies that might arise. What I did not talk about was how we actually generate the Markov chain, how we choose that transition operator. So what I'm going to talk about until the coffee break is previous attempts to do that, why they fail in high dimensions. That's going to motivate Hamiltonian Monte Carlo. But before I do that, I want to break to see if anyone has any questions. Give myself a chance to drink some water. No questions? Everyone's good?
So you mostly don't know computing expectations with the MCMC. But also very often they are interested in critical intervals and interval estimates.
Yeah.
So do you have similar guarantees in the form of central linear like that for
yeah.
critical estimates?
So the so from the Bayesian perspective, you're not computing confidence intervals, you're computing credible intervals. But those are just quantiles. And quantiles can be written as expectations, and they satisfy the properties of the Monte Carlo central limit theorem. So the only thing you have to be careful about is the order of the quantile. So if you're looking at the median, that's pretty consistent. If you look at the 95% quantile, it's just a little bit noisy. So the Monte Carlo Standard Error tends to be a little bit high for those. But they do satisfy all the properties, and they tend to be particularly good estimators.
So you mentioned the difficulties with multimodal theories.
Yeah.
And it seems like, so Hamiltonian Monte Carlo anticipates going to improve when you have a unimodal
Right.
posterior.
Right.
So in the high-dimensional problems that you're interested in, do you find much multimodality, or?
Yeah. So okay, I'll give my very brief blurb on multimodality. A lot of times people come up to us and say, look, I have this machine learning algorithm, and I have 2 to the k modes where k is 1,000. Can you fit all the modes for me? Even if you had an algorithm that could explore that, there's no way you're going to run an algorithm that can run for 2 to the k iterations, right? It's just completely meaningless. So what we focus on is trying to build models that get around the multimodality. So if you have things like combinatorial multimodality, you can put an ordering on your parameters, and that will kill a lot of the multimodality. So this kind of combinatorial multimodality is a bad modeling choice, and there's ways around it. Now that said, especially in scientific perspectives, there are modes you just can't get rid of. There are very meaningful non-identifiabilities in your data. And for cases like that, sometimes things like HMC will be okay because it does have a means of getting out, but it may not be super efficient. And in those cases, you have things like nested sampling. I'm not going to get a chance to talk about it, but there's some new stuff we're working on where we're kind of improving tempering that it can explore modes in the Hamiltonian-like perspective. So it's not a game for MCMC, right? MCMC gets you these nice constant expectations by assuming that the global structure is equivalent to the local structure. And multimodality breaks that assumption. So you'll never, ever see a proof of ergodicity in multimodal systems. Yeah. So if you know you have multimodality, look at things like nested sampling and these tempering algorithms, or these thermodynamic algorithms, which should be in Stan in like 6 months or so.
Distinguish between these two sorts. One is like something that came out of a bad model choice.
Yeah.
And another is genuine.
Yeah. Yeah. And that's why modeling is really important, right? So just throwing down an algorithm, you don't necessarily inspect those kinds of subtleties. Yep.
About this topology showed when things go better in the upper half and stack in the center. Should kind of this topology disappear if you run the chain sufficiently long time?
No. This is the problem. So it's not that you're not running long enough. It's not that you're random walk exploring and you just happen to randomly turn around there. There's an actual physical pathology at that region, in that neighborhood where the chain breaks down. So what's actually happening is there's a very high curvature, and the length scale of your transition is way too long. And so you just don't have enough resolution to look into there and get into this little narrow window. So it's a real fundamental problem.
Yeah.
So in the beginning of the lecture, you talked about the volumes growing bigger as the dimension grows bigger. I don't quite understand that. Could you give an example about the 2D and 3D?
Okay, so for the Gaussian case, we have spherical symmetry. So the surface area of say in 3 dimensions, right? The surface area of a sphere goes as 2 pi r squared. Right, and so the differential volume of a shell is going to be 2 pi r, right? I haven't done this in a long time. 2 pi r. I'm going to the Simpsons episode with RDR. Anyone remember that? It's the differential of pi r squared, right? Yeah, so it's 2 pi r dr. And so it's that r factor, right? You can think about it as Jacobian, you think about it as volume factor. But from the spherical symmetry perspective, that's going to grow as you get bigger and bigger. So just imagine you have a shell, right? So if the width of that shell is the same, as you get further and further out, it's more and more surface area. So it's tricky, great. So the concentration measure is really hard to interpret, but it happens all over the place. So cubes, if you put uniform density on a cube, all of the mass goes to the corners. This is why the Ising model is really hard. Because even if you have uniform density, you get into this case where it's completely multimodal, and there's no way to transition between the modes, because there's no probability density mass between them. Any other questions? Yeah.
You basically said that we have to inspect our chain before we actually run our experiments, that it's mixing correctly and everything. So what about us machine learning guys who have to fit distributions to their data? So we have to basically run 10,000 times a Markov chain, so we can't actually look every time that our chain is consistent, because we do a sampling step and then we change the distribution.
So you don't actually look and then say, okay, I'm okay to sample. What you do is you set a warm-up time, you set a sampling time, and then you look at the sampling region and see if it's consistent with convergence. And if it's not consistent with convergence, then you either have to kill some of that initial sampling time to throw it away as part of convergence, or you rerun with a larger sampling window. So there is some iteration there, but usually you can catch it pretty quickly.
But this requires basically human intervention at like every chain.
Yes. So yes, technically it can change for every chain, but for the most part, you can identify what's going on, right? It's pretty easy to overestimate the warm-up iterations that you need, and very rarely do we run into cases where we have to keep running, and waste all of our time trying to do warm-up.
Okay.
Yeah, about convergence. So, I mean, these diagnosis tools that you they will work really well if you have simple problems in the graph, like you said. Once you move to the upper right-hand side, this gets kind of tricky, right? Diagnosing whether you have converged or not. So sometimes, it almost seems as hard as the original problem in the sense that you basically have no idea of convergence, and these diagnosis tools, they won't tell you anything. And you know what I mean? It's kind of a chicken egg problem.
So I would agree with you if you were running something like random walk metropolis or a Gibbs sampler, right? Where we have these huge autocorrelations, and the problem is our diagnostic is another expectation, and if we don't run it for long enough, we have the same kind of pathologies that might be arising. But when we go to these advanced algorithms like Hamiltonian Monte Carlo, where we have very low autocorrelations, those expectations are very robust, even in high dimensions.
But I mean, if you have like a model that has very complicated nonlinear interactions between hundreds of thousands of variables, then, I mean, how in the world do these convergence statistics work?
It's the same thing with an expectation. You can look at the diagnostics and you can identify if it's exploring fully. So if you have crazy nonlinearities and your chain is really poor, or if your transition is very poor, then your chains are just going to kind of get stuck, and you can your R hat is going to be terrible. So in fact, in high dimensions, it becomes harder to pass these constraints. So they tend to remain very robust in high dimensions. Okay, so that was a lot of questions. So I'm going to have to whip through HMC really quickly. But it's okay because it's all math. So this is where things get tricky, right? So we know hopefully I've convinced you that MCMC is really important for high dimensions, but we have to then choose this transition operator. And Anne talked about random walk metropolis, the Gibbs sampler. Amir talked about the Gibbs sampler. They're really, really bad in high dimensions, and I'll show you some examples of what's happening. And then very quickly motivate HMC. And now this is where things are going to get tricky, because the motivation for HMC is very, very solid, but it's super mathematical. And it's very hard to get that intuition across unless you've done a lot of differential geometry. So I'm going to invoke the magical theorem a little bit. Do you guys know the Arthur C. Clarke quote? Any technology sufficiently advanced is indistinguishable from magic. So it's the same holds for algorithms. Any algorithm sufficiently advanced is indistinguishable from magic. So pretend I have a nice suit and tie on and just take it for granted. Okay, so random walk metropolis. This is the guided diffusion that Anna was talking about. The way I like to physically think about this is you have a point, and it's going to diffuse out, right? So it's going to kind of random walk, drunkard's walk, and slowly expand. And the trick here is this correction. This is called the metropolis acceptance procedure. And what it does is it corrects the diffusion so you always converge to the right target distribution. This is the part that guarantees that for any target distribution, you're getting the right samples. So you're kind of randomly going outwards, you stop, and then if the density is higher than where you started, you always accept it. So it's got a little bit of an optimization feel to it. But at any point you have a lower density, you have some probability of accepting that jump. So again, think about it like you're kind of randomly going out. So you're in a dark room, you have no idea what's going on, and you're just walking awkwardly and bumping into stuff, right? And you're getting where you need to go. So that's random walk metropolis. No surprise, it's going to be really inefficient. Now, the second thing is the Gibbs sampler. Now, people love the Gibbs sampler, statisticians in particular. This was the top of the walk through the 80s and the 90s. And it's interesting, kind of the sociological reasons why people like this. But so it requires these conditional samples. So instead of making a joint update of the space, we're going to make these conditional updates. So if I have a two-dimensional distribution, I need a parameterization. So if I have parameters theta 1 and theta 2, I sample theta 1 given theta 2, and then I sample theta 2 given theta 1, and I repeat that over and over again. The first thing you should immediately recognize here is this requires a parameterization, right? So it should be bad. There should be some pathology arising from the fact that it's sensitive to a parameterization, just like the modes. And indeed, there will be some problems. Now, to demonstrate the efficacy of these algorithms in high dimensions, we're going to have to be a little bit careful. I cannot show you a million-dimensional distribution. Really hard to get a projector with that kind of technology. So what I'm going to do is appeal to this intuition of a typical set. So if we have this concentration of measure, what's going to matter as we go to these high-dimensional systems is we're going to get nonlinearities and non-convexities, right? So we need to explore from something like this and not the nice spherical thing. So to demonstrate that, I'm going to look at this annulus. It's not a perfect analogy to what happens in high dimensions, but it has nonlinearities, right? There's very large radial curvature. There's no azimuthal curvature. So we get that nice nonlinear change as we go around, and it's very, very non-convex, right? There's a giant hole in the middle. Can't get any more non-convex than that. And if I run random walk metropolis, you can see what's going to happen. So if I want a reasonable acceptance probability, I need to have a very small length scale on my diffusion. So that's going to lead to slow exploration. But look what happens down here. It's getting stuck by the non-convexity. So we have this double whammy. The exploration is really slow because I'm doing this random walk. I can't go very far. And then because of the structure of these high-dimensional distributions, I tend to get stuck in places. And so those can compound onto each other and lead to extremely poor exploration. So even if we can find the typical set, we explore it very slowly. It leads to large autocorrelations, poor Monte Carlo estimators, and bad inference. Right? This is why MCMC oftentimes gets a bad rap in high-dimensional models, because you're running a bad transition operator. And the Gibbs sampler is no better. So because we have these nonlinearities and the non-convexities, the conditional transitions are very, very short and stunted. So we get the same kind of problem of slow exploration and getting stuck. Now, excuse me. Another way to see this is to think about how the transition operators are exploring. So this is a 100-dimensional Gaussian distribution. This is just a two-dimensional projection of it, very highly correlated. Now, if I want to explore the entire typical set within a single transition, that's what I need for an independent sample. Marginally, what kind of exploration do I need? What do I have? Right, so I need to explore all of this. Now, this is going to be hard because there's giant swaths of nothing. But if I want an independent sample, I need marginal variances, right? Marginal is important here. I need to integrate over everything at this big, wide expanse. But random walk metropolis and the Gibbs sampler don't explore marginal variances. They explore conditional variances, right? So locally, depending on where you are, you're limited to this very, very tiny window of exploration. And so what happens is you can't go very far within a single transition. So you have to apply another transition. But every time you apply another transition, you're adding new randomness into the system. So if I have to go from here all the way up there, I can't just do it in n steps. I get n squared steps, or maybe n cubed steps, depending on the dimensionality of the system and kind of how your eigenvalues go. So the problem with these algorithms is that they explore with these conditional variances. And because there's randomness induced at every iteration, we tend to get incoherent exploration, right? It's this random walk behavior of the exploration that's killing us. So if we want to do better, if we want an algorithm that's going to scale to high-dimensional systems, I need coherent exploration. And it turns out this is really, really hard. How the hell do I take some local point and let it explore this incredibly complex high-dimensional thing that I have no idea what it looks like? And this really held back inference for a long time. That's random walk chops in the Gibbs sampler. Again, slow incurrent exploration. So the key so remember, we want coherent exploration. The key to coherent exploration is an understanding of the geometry of your system. So imagine, for example, at every point I could put down a little arrow. Now, what's the first thing you want to do when you look at a plot like this? If I gave you a marker, what instinctively do you want to do? I mean, yeah, right? You want to connect the dots. And that's what we want to do too. What this structure allows us to do is literally connect the dots. So this vector field admits these integral curves, which is a fancy way of saying connecting the dots. And what this gives us is the ability, if I'm here, I can just follow that curve up and go all the way to the other side of the space. If I'm over here, I can follow this curve and go all the way across the other side of the space. It's this kind of vector field construction that gives us the coherency that we need for good exploration. Now the only trick is, how do I take a probability distribution and put arrows down everywhere so it follows the typical set? And that turns out is really, really hard. There's a lot of ways you can try to do it, and they all fail. There is one very particular way of doing it, and it magically brings us into physics and all kinds of nice things that aren't going to be helpful for a machine learning audience. So this is where the magic comes in, all right? So just take my word for it. We need to double our space. So we can't do it on our original space. We have to expand what we have. So for every parameter q, I need to add a momentum, p. The momentum, again, comes from that physics analogy. So we have this bigger space. And the magic is that for any scalar function, so any function of my original parameters and my auxiliary parameters, this measure, again, a density times a volume, this measure is preserved. So we get arrows that guide, we get little arrows that we can connect that are going to follow the mass of this thing. And so all we have to do is somehow choose a target measure on this expanded space, write it in a form like this, and then we can follow those curves and get the exploration we want. And that will give us a Markov transition. So if I have some position in parameter space, I randomly sample the momenta, I run this evolution for some amount of time, and then I stop. I throw away the momenta, and I have a new point. That's the Hamiltonian Monte Carlo transition. Now, the key to this transition is to be able to throw the momenta away at the end. In order to do that, we have to be a little bit careful at how we choose our function, our distribution on this bigger space. So if you recall that our target distribution that was invariant, our density that was invariant, was e to the minus h. In other words, h is minus log of the target density. If I want to be able to throw the momenta away, I need to be able to integrate the momenta and get the target distribution. So the marginal has to be our original target distribution. This is the most general way of writing this out. Right? So you throw the product rule down, and this means if I come in with an integrate against the momentum, that term integrates to 1, and I'm just left with pi of q. Right? And because I have logs, that's going to split up into two terms. So, yeah.
From where do you know the momentum models?
Yeah, so exactly, right? So because of this construction, I know this. This is completely unspecified right now. Right? I don't know how to do it yet. And this is going to be important because there's multiple ways of choosing that. So this term here that depends on the momenta, the conditional distribution of the momenta, we're going to call T, or the kinetic energy. And as was pointed out, we don't know what this is yet. This is completely unspecified. The only thing that's specified is this potential, or V. And that's given by the target distribution. So Hamiltonian Monte Carlo is this generic construction, and we're going to get specific implementations based on how we choose the kinetic energy. And the simplest thing we can do is choose it to be a Gaussian. Right? It's the canonical go-to. And if we do that, so we have a Gaussian that's independent of position, so it's a constant covariance everywhere. The kinetic energy looks something like this. We get this kind of interesting quadratic form. Now, what's really nice about this is it has a nice physical interpretation. This is the kinetic energy from classical mechanics. And so the space that we're working on is something called the Euclidean manifold. And so we had Hamiltonian Monte Carlo is the generic construction. This particular implementation is Euclidean Hamiltonian Monte Carlo. Right, so be a little bit careful about the notation here. Most of the literature is not careful about the notation. So if you've previously read any of Radford Neal's papers or the other literature on HMC, almost all of them are this Euclidean HMC variant. But we're going to be a little more careful about it because we're going to have other choices as well. Now, I'm going to take that metric, the mass, the covariance, to the identity, and I can go back to the annulus, and we can immediately see the utility. Because we're connecting the dots and we're getting that coherency of exploration, I don't have a random walk anymore. I'm not getting stuck. I get really, really nice coherent exploration. I stop somewhere and I get essentially an independent sample. Right? This is going to be the key. You get these very, very nice smooth trajectories. And I go back to the Gaussian case where we had this very, very incoherent slow exploration. So these are thousands and hundreds of transitions. If I run an HMC with tens of transitions, I explore everything. Right? The guidance of that vector field that we can connect the dots on is the critical thing here, because it guides us along the probability mass and ensures that even in high dimensions, we stay concentrated on that probability mass. Now I'm going to, this is Euclidean HMC. When we talk about Stan and other implementations, we're only ever going to talk about Euclidean HMC. But I would like to just very briefly mention some of the research that we're working on to make this even better. So Euclidean HMC is great, but there are some weaknesses to it. And the first weakness was already evident. Can anyone identify what might be oddly efficient here?
It's not actually random.
That's not an issue. So this trajectory is deterministic, but the initial momentum is random. So if I had resampled the momentum, I would have gotten a completely different trajectory. So that's not a problem. Everything's completely ergodic and not an issue. There's a computational problem here.
I mean, your set is very wide in context for moving out.
Yeah. So the issue here is the nonlinearities are manifesting as this transverse oscillation. So we're spending a lot of time oscillating up and down when we really just want to be moving in the angular direction. It works, right? It's just perhaps not as computationally efficient as we might want. But this is trivial compared to the big problem. And it's a little bit subtle, so please bear with me. The really nice property about these trajectories is that Hamiltonian function is constant. Now that means that the kinetic energy and the potential energy, the log of those two distributions, those have to sum to 0. So if the kinetic energy goes down, the potential energy has to go up, and vice versa. So the variations of those two have to be the same. And the problem is that for that kinetic energy, that Euclidean kinetic energy, it can only vary by half the dimensionality of the system. So if I have 100 dimensions, the potential energy can only vary by 50. Now, potential energy is the log of the target density. So the target density can only vary by about 20 orders of magnitude. Right? That's a lot of orders of magnitude. Right? We're talking about Avogadro's number of thermodynamic kind of orders of magnitude. But in high-dimensional probability distributions, that's nothing. And the canonical example is a hierarchical model. So this is something that Anna also mentioned. These are badass models. These are incredibly useful when you're trying to do big, complex analyses. You take like a logistic regression and make it hierarchical, and it gets exponentially better. And the main utility is this conditional dependent structure where even though these x's might be completely independent variables, because of this latent structure, they can learn from each other. We get partial pooling and all kinds of great statistical properties. The pathology, though, is that because they're all connected, if v changes by a little bit, all of those x's change in the same direction. Right? So there's a coherent motion of the densities that all add up. And in fact, if we had another layer, we'd start getting exponential amplification as we go higher. Same kind of problem that you see in deep learning, basically. Right? Deep learning is just a hierarchical model. So if we apply HMC to this, here I'm going to use the funnel. This is our canonical example of a hierarchical model. We have 100 x's, so just rotate this in a 100-dimensional space. We have one latent v that controls the variance of the x's. If v is small, we get small variances on the x's. We have a lot of probability mass concentrated at a very high density and a very small volume. If v is large, we have our probability mass distributed over a much wider volume at a much lower density. Right? So where's the typical set for this thing? Don't have any guesses? Sorry? What, like, direct my hand. Here? Okay. Sort of. So that's part of it. Right? But the magical thing here is that variation, the density is going down and the volume is going up. They exactly compensate for each other. So we actually have a very wide typical set. It looks something like this. And if I want to draw an independent sample, I have to explore all of this. Incidentally, do you know where the mode of this thing is? It's at minus 550. Meaningless, completely meaningless. All right, so I need to explore an entirety of this thing, but the density changes by 250 from the top to the bottom. 101 dimensional, so I can only vary by about 50, right? So how much of this can I explore? $50 divided by 250, right? So I get about a fifth, right? And if I run the trajectory, I see I get exactly a fifth of what I can explore. So we have this very awkward constraint that limits our exploration in these hierarchical-like models. Now, that's OK. We can run more transitions, and we'll eventually explore everything. But we get back to this random walk behavior. It's much better than random walk metropolis of the Gibbs sampler, but it's not as good as it could be. I'm going to have to whip through this really quickly. But the solution is to have the covariance depend on position. This means that this gives us local corrections that should correct for the curvature. That should get rid of the transverse oscillations. And then this normalization constant that we threw away before because it was a constant now matters because it depends on position. And the beautiful thing about this is really cool. We did not put this in because it had any purpose. We put it in to be mathematically consistent. And then after the fact, we realized what was happening. This thing acts like a capacitor. When you're in a region of high curvature, this term gets really big, and it sucks up a bunch of energy. And then when you're in a region of low curvature, it releases that energy back into the system. And that compensates for those little variations in potential. So if I go back to the annulus and I run the trajectory, get a nice targeted exploration. We have no more of the high-frequency oscillation. Position-dependent metric Instead of Euclidean, we now have a Riemannian space. So this is the infamous Riemannian Hamiltonian Monte Carlo. And the really cool thing is when we go to the hierarchical model, we now get these sprawling trajectories that cover the entirety of the typical set. So now we're back into this regime where we can get independent samples, really, really effective high-dimensional inference, and really, really pretty pictures. Now, this is all great, right? We have our algorithm. It goes to high dimensions. And everyone should be using it, but they're not, right? There's HMC's been around since the 80s in the physics literature. It's been around in the 90s since Radford Neal introduced it for Bayesian neural networks. And for some reason, statisticians are really scared of it. There's a reason for it, right? This is not, I'm not trying to be facetious here. HMC is really tricky, not because it's hard to understand, but because it's hard to implement. So to see that, let's consider what we actually have to do. So we have these trajectories. Turns out they're given by the solution to ordinary differential equations. So we have to solve something like this. Okay, that's not too bad. We're not going to get analytic solutions. We have to do numerical integrator. That's fine. We're all comfortable with numerical integrators. We use a fancy numerical integrator called the leapfrog. Integrators have all kinds of nice properties. But again, who cares? Someone tells you to do it, you do it. We have an error now, so we have to do a metropolis correction to make sure that the error doesn't affect anything. So we have something like this. Again, it doesn't really matter, the details. What matters is that we have maybe something that you can code in like 40 lines of R, or Python, or C, or whatever you might want to do. The algorithm itself is extremely simple. The problem is not the algorithm. The problem is all these little parameters in between. So not only do you have to specify your target distribution, okay, that's not really a fair criticism because everyone has to do that, but we require the derivative. This is now starting to run into problems. I did HMC first in my graduate thesis and would sit down for weeks writing out pages upon pages of nasty derivatives and coding them up, getting them wrong and recoding them up and getting them wrong. You can't expect that for, if you want a general tool, it's not the way it's going to work. Then we get things like the metric. How do I choose that? If I choose it wrong, HMC is going to be really, really bad. What about the step size of the numerical integrator? If it's too big, I'm going to get lots of error, and I'm going to get lots of rejection. If it's too small, I'll get a high acceptance, but it takes me forever to go anywhere. So there's hopefully some compromise in between. But how do I choose that? Does it depend on my target distribution? Do I have to retune it for everything I do? And then there's the magical thing that I kept going over. When do I actually stop integrating? Right? If I don't go far enough, I'm basically random walking again. If I go too far, I end up coming back to where I started. So there's all of these parameters, and if I don't choose them correctly, I can get a really bad algorithm. And this is the real problem with HMC. And it's exactly the motivation for STAN. So STAN is our platform for Bayesian inference, as we're calling it. It's an implementation of HMC with three very, very important tools. We have a modeling language that allows you to specify a complex distribution very, very simply. It's a probabilistic programming language. We have an automatic differentiation implementation that does the derivatives for you. And then we have a suite of adaptation routines that tune all of those parameters. So in most cases, you can run STAN and not have to worry about any of that stuff that I mentioned. All you have to do is write down your model. We'll do the algorithm. We'll do the tuning. So let's just very briefly whip through these. The modeling language, as I mentioned, it's a relatively simple probabilistic programming language. It's based off bugs, if any of you guys have played with that before, only it's actually like structured well. So it's static, it's statically typed, it's strongly typed, it's much more rigid, which allows us to catch a lot of errors ahead of time, which is great. And I'm going to be spending the next talk getting a lot more in depth about the modeling language and a lot of the features that we have for doing really good inference. So that's the modeling language. The language gets parsed into C++ and then compiled down. So this is not interpreted. This is also the reason why it's kind of hard to install Stan, because you need to have an active compiler. We compile this down to very efficient C++. That gets compiled to machine code, and so we get very efficient implementations. And then as we're doing that, we also play some magical games with the autodiff. So Joshua mentioned autodiff briefly when he was talking about the deep nets. Theano's a little bit of a different beast. Theano has some symbolic stuff in it as well. We use automatic differentiation just for computing the numerical derivatives. And it's a very, very efficient implementation where we can get those gradients analytically. Well, not analytically, but we get the exact gradient numerically. There's no finite difference magic going on here. This is another one of the things where people tend to think is magic. It's not magic. What it's doing is it's separating out the algebra of the chain rule from the partial derivatives. So if you've ever done a big nasty chain rule calculation, you have all these little partials. And what's hard about it is organizing all of this nested algebraic structure. And what the chain rule allows us to do is factor that algebraic structure out, automatically implement it recursively, and that gives us something like autodiff. So if a computer is going to compute something like this by computing two partials, x squared plus x squared and y squared, those partials go into a plus, which gets stored in a temp, right? That's kind of how the stack gets built. The same way you can evaluate the partial function evaluations, you can also throw in the partial derivative evaluations. And that gives us the autodiff. But again, you shouldn't have to worry about it because it's all automatically done. And then the adaptation. So let me kind of breeze through this. The beautiful thing about the Hamiltonian Monte Carlo structure is that the mathematics informs us how to tune everything. And so we get these very nice bounds like this, where this is the relationship between the average acceptance probability and the cost, which allows us to tune the step size. This is for almost any target distribution. And so if we're up in this region over here, it doesn't matter what you're doing, we know how to bound that extremely well. And that gives us a very global generic means of tuning the step size. The integration time is a really tricky beast, because this is not something that's local. Or sorry, it's not something that's global. It's not something we can tune during warm-up, because the optimal integration time might depend on where you are in space. So imagine we start at some point. What we'd like to do is integrate forward until we see this little turnover. We don't want to come back, because that's going to be wasteful of computation. But I can't do that. If I stop there, I break detailed balance. I no longer converge to the right target distribution, and I'm screwed. And so the really, really clever thing that Matt Hoffman came up with was to not integrate forward in time, but to actually randomly integrate forward and backwards in time. And you do it with this binary structure, so you build up a tree. And the tricky thing here is if you apply any kind of stopping criterion recursively through the tree, you can preserve detailed balance exactly. So this is a really, really clever technique that allows us to automatically stop the chain. So this is the no U-turn sampler, which is what we end up using in Stan. And Stan's only a few years old, but the ability to automatically tune all of this nasty stuff and then allow this scalable inference to high dimensions has become very, very popular in a lot of fields. So we're very, very excited about a lot of the implementations. And it's been everything from political science, social science, epidemiology. We had a really cool astrophysics thing that came up a few weeks ago. Plant science, anthropology, ecology, et cetera. So this is what we're really excited about, because this is our audience, right? We're looking to make this inference available to actual users. And hopefully, maybe some of you guys. OK, so I whipped through that very quickly, because for the most part, you don't have to worry about any of it, right? You just have to know that it's there. So this and this, forget about it. What we're going to focus on for the next talk is the modeling language, because this is what you need to know to actually specify something. So what we're going to do after we come back from the break is I'm going to go over the modeling language. We're going to learn some of the features, some of the nice properties, and then we're actually going to build a model. We're going to fit some nice Gaussian processes, do some interesting things, and hopefully give you guys a chance to learn the language and do something cool. But until then, we're already 5 minutes late for coffee, so go get out there and be prepared to come back.